So this week is first class back from vacation, from spring break. Thought we'd talk about steel, kind of going from site work to concrete to steel, more or less in the order that the building construction would go up. And the next class we'll talk about wood, timber framing, and light wood frame construction. And we'll talk about exterior finishes, interior finishes. We'll probably finish up with doors and windows, that type of thing, and see where it goes from there. Mostly the building structure is what we're looking at this semester. So steel, this first couple of slides I pulled out of one of the textbooks I've used in the past, and I'll read through these first couple and then we'll kind of skip through the rest of it. This will be available for download as a PDF file, so you can use it as a study guide. Steel is of a range of alloys of iron that contains less than 2% carbon. Ordinary structural steel, called mild steel, contains less than 0.3% carbon. The less carbon, the less brittle. Plus traces of beneficial elements such as manganese and silicon, and of detrimental impurities such as phosphorus, sulfur, oxygen, and nitrogen. In contrast, ordinary cast iron contains 3 to 4% carbon and greater quantities of impurities than steel, while wrought iron contains less carbon than most steel alloys. The difference between basic iron and wrought iron is the fact that wrought iron is actually hammered to release some of those impurities and make it a little more flexible. The carbon content, of course, is crucial to the properties of ferrous. The name ferrous refers to iron-based metals. Too much carbon makes it hard and brittle, like cast iron, while too little produces a malleable, relatively weak material. So there's a fairly fine balance in that structure. A little history of steel. Prior to the 19th century, metals had little structural role in building except as connecting devices. The Greeks and Romans used bronze to make little clamps to hold stone joints together. Architects in the Renaissance countered the thrust of masonry vaults with iron chains and rods, basically laid in the ground to prevent structures from spreading. The first all-metal structure, a cast iron bridge, was built in the 18th century in England and still carries traffic across the Severn River more than 2 centuries after its construction. Cast iron produced from iron ore in a blast furnace, and wrought iron that has been purified by beating it repeatedly with a hammer, were used increasingly for framing industrial buildings in Europe and North America in the first half of the 19th century. The usefulness was limited by the unpredictable brittleness of cast iron and the relatively high cost of wrought iron. If you had to hammer it, it's going to be very labor intensive, and really the manufacturing process didn't really come around to the point where it was economical to use this type of material. Until that time, steel had been a rare and expensive material produced only in small batches for such applications as weapons and cutlery. Plentiful, inexpensive steel first became available in the 1850s with the introduction of the Bessemer process, in which air was blown into a vessel of molten iron to burn out the impurities, and by this means a large batch of iron could be made into steel in about 20 minutes. The structural properties of the resulting metal were vastly superior to those of cast iron. Here's a picture of the part of the Eiffel Tower, and we're going to talk about the open hearth method, developed in Europe in 1868 and was soon adopted in America. By 1889, the Eiffel Tower was built of wrought iron in Paris. Several steel-framed skyscrapers had already been erected in the United States, and this new material known as steel had been born. This structure, you can see it has a brick exterior, but it's actually a metal-framed, one of the earliest skyscrapers in Chicago, circa 1893. Here's the manufacturing process. The steel it is converted, most steel is converted from iron, manufactured by the basic oxygen process, in which a hollow, water-cooled lance is lowered into a container of molten iron and recycled steel scrap. Within that lance, a stream of pure oxygen at very high pressure is blown from the lance into the metal to burn off excess carbon and impurities. And then a flux of lime and fluorspar is added to the metal to react with other impurities, particularly phosphorus and forms of slag that is discarded. And then they can add things to the material like manganese for abrasion and impact resistance, molybdenum to give it strength, vanadium imparts strength and toughness, and then we add nickel and chromium to give it corrosion resistance, such as stainless steel. And the entire process takes place with the aid of careful sampling and laboratory analysis techniques to ensure the finished quality of the steel, and it actually takes less than an hour from start to finish. Here's an illustration of the process. We can start up here at the top where we've got iron ore, limestone, and coal go through coke ovens or crushers, and this becomes material that gets put into a blast furnace. That material goes into molten iron that's put through or added with oxygen, lime and flux, and scrap through these materials and combined to come out into a molten material that can be cast into a rough shape that it needs to be. Goes through a bloom mill. This is basically your material that is going to be extruded or run through rollers as it goes down through this breakdown stand and the pulpit and roughing stand. You can see the shape of the steel going through these rollers in its semi-molten state, so it becomes the structural shape that you're looking for. So it's a very intense, high energy use process that's used to create the steel elements that we're looking for. This is a photograph inside a steel mill. You can see a large wide flange beam coming out of the system. It says, today most structural steel for frames of building is produced from scrap steel in so-called mini mills, utilizing electric arc furnaces. These mills are miniature only in comparison to the conventional mills that they have replaced. They are housed in enormous buildings and roll structural shapes up to 40 inches deep. The scrap from which structural steel is made comes mostly from defunct automobiles, one mini mill alone consuming 300,000 junk cars in an average year. Through careful metallurgy testing and quality, these are recycled into top quality steel. So all those impurities get burnt out of these Subarus and whatever else gets into this steel, and it is a highly recyclable material, although it takes a lot of energy to recycle a material. Our structural shapes that are used for the building construction industry are kind of shown here in its basic form. We have American Standard, which has an S designation. Our wide flange beams, which have W designations. We have C designations for channel steel, L designations for angle, and angle comes in unequal legs or equal legs. Structural T, which is basically half of a wide flange beam, and you can see it has a WTS designation. We have our basic plate steel, our bar steel, our round stock, and our bar stock. This would be square bar stock and rectangular bar stock. The designations on the numbers on all of these indicate, or not all of them, but the channel, the wide flange beams, and the T's, or at least the, not the T's, the first designation number indicates the height of the steel from top to bottom. The second designation is the weight of that steel in pounds per linear foot. So a W10 by 12 would be 10 inches tall, 12 pounds per linear foot. This one is 10 inches tall and 30 pounds per linear foot. So here we have the definitions. Wide flange beams, W21 by 83. W denotes the wide flange shape. First number is the nominal depth in inches, and the second number is the weight in pounds per foot. Same was the S designation, the channel. This one, MC10, would be 10 inches tall, 33.6 pounds per linear foot. We get the nominal dimensions that these pieces of steel are available in. The structural T, that might have been a 5 on the previous page. WT denotes the T shape. 13.5 is the nominal depth in inches again, and then 47 is the weight in pounds per linear foot. The angle does not have that designation. The angle is just an L. It gives us the designation for the one leg, a second designation for the length of the second leg in inches, and a thickness of the material in inches. L4 by 3 would be a 4 inch by 3 inch angle, 3/8 of an inch thick. And then we have HSS, which denotes hollow structural section, and this could be tube steel in square, rectangular, elliptical shapes. That is also used. You might use this for a column in a small building. Sometimes we use round columns for basement areas in residential facilities. And again, the wall thickness is the last designation. So this 10 by 8 would be a rectangular hollow steel shape, 10 inches by 8 inches by 1/2 inch. The manual for steel structural shapes, this is just a page I took out of that manual, and we can see if we look at a W12 by 58, the area is 17 inches square, 17 square inches I should say. The depth D is 12.19, so this depth from top of flange to bottom of flange is 12.19 or 12 1/4 inches. They give us both decimal and fractional dimensions. The thickness of the web in this case is 0.360 or 3/8 of an inch, and that is this dimension right here. This is the web of the steel, and this is the flange horizontally, top and bottom. So we got one web, two flanges. The flange width is 10.010, and that is this dimension from this edge to this edge, nominally 10 inches. The thickness of the flange, 0.640 or 5/8 of an inch, and that's this distance here. This TF is the thickness of the flange. And then we have the distance, 9.5 inches is your T dimension. This is be inside the radius on both sides. So that T dimension is fairly important. If you're cutting other steel to fit into this area, you need to know where the tangent point is between that curve and the straight edge of the web. And then we have a K1, which is distance from the top of the flange to the inside of the arc, and then K1 would be from the center line of the web to the inside of the arc. So both of those dimensions are given for each particular type of steel. If you're a detailer, you're going to want to know this information. Most computer programs now have these sizes already in their system, so you can just grab what you want, put it in, and it's going to come in to scale. Same thing with angles. We can see there's an L4 by 3 by 5/8. They give us a chart with different dimensions located on it, and we can get our dimensions using these letter designations. For instance, the Y dimension would be listed here as 1.37, which is the distance from the bottom to this point where it intersects this piece. And that has to do with your sizing. But the overall length of these legs, 4 inches from top to bottom, 3 inches in this direction. So these are all properties for designing. A lot of these angles and shapes are used in combination to create other types of steel shapes. For instance, open web steel joists. If you look at the bottom and the top of these, they're actually angles that are back to back, and then they have these webs which are either tube steel or solid material or other angles into two angles back to back on the top, and these produce what are known as open web steel joist, OWSJs. Mass-produced trusses take much less weight, are able to span fairly long distances, less labor and materials to put them together. Of course, they're less expensive, And we can see here there's a couple different designations. We have a K-series joist for spans up to 60 feet. We have an LH series designated as long span, and it can span up to 96 feet. And then we have DLH, or deep long span joist, which can actually span up to 144 feet. So some of these open web steel joists can be used on very large buildings, and depending on their spacing, be spanning quite long distances. When we look at steel, we're talking about beams, girders, which are horizontal members, columns, which are your vertical members that they fasten into, and we need to determine how those are going to be connected. The older method of fastening steel together would be using rivets, where a rivet is a steel fastener consisting of a cylindrical body and a formed head. They bring it to a white heat in a forge, insert it through the holes in the members to be joins, and I work with a pneumatic hammer, actually heads over the other side to bring it tight. And as it cools, it actually shrinks and actually becomes tighter as it cools, so that it brings the steel even closer together. A little labor intensive and slow. In more recent history, we've come up with other ways to fasten steel together, and one of those methods that's fairly common today is a tension control bolt. It's important that when we fasten steel together, that it is fastened together consistently. So these tension control bolts are designed to provide a certain PSI strength. And what happens with these is you would use a wrench, a pneumatic wrench like this, that goes over this spline on the end, and it actually turns the bolt counterclockwise while it holds the nut in place. And as that turns, what happens is it will reach a certain torque or tension, and the soft metal on that spline will break off at that particular tension point, and then you just drop the end out. This allows you to very quickly and easily put a lot of bolts in place, and you are assured that they are tightened to the proper tension or torque in the steel. We actually, in the construction process, we have people that go out to the steel framing and check the bolt connections to make sure they are tightened properly, and they'll do that within certain areas. They'll kind of pick and choose which ones they test, and really kind of give you a second look to make sure everything is tightened down to specifications. So we've talked about rivets and bolts, and the other method, of course, is welding. Electric arc welding is very simple. We basically put an electric current through an electrode that has flux on it. It creates heat, melts down, and actually melts into the existing component, creating a metal weld that fits over the top. It will have a kind of a crust on the top called slag, and then that puddle is kind of drawn across. When we're drawing this type of material on plans, we have to be specific about what type of welds we want. So if we look at this chart, we can see some symbols that are used in the drawing process to indicate how welds are to be applied. We have, first of all, these simple welds where we have a back weld, a fillet weld, which is the most common that you'd see, plugger slot, square welding, V welding, bevel welding, and different types of flares. You're going to point to an object on the drawing with this arrow. This flag means it's going to be welded in the field. And then out here would be your designations for fillet weld or whatever. This circle at the joint indicates weld all around, and that could be combined with the field weld. You could have a flag and a circle. The M indicates a backup bar. The M inside the line indicates a spacer. So if we look at this sharp bend near the end of the arrow, indicates that the arrowhead is pointing toward the groove side of the bevel, or J groove. Now if we look at this, we can see in an illustration how these work. We have a bevel groove or V groove weld with a backup bar. There's our backup bar. The steel has been ground at an angle, and we're going to fill this opening with a V groove weld. Over here we have a backup bar with a single bevel groove weld, so it's basically a 90-degree right triangle we're going to run this through. And then of course we have our fillet weld, and this is just two pieces of metal that are butted up against each other, and we run the bead of weld across. So when we see this symbol, it's interesting to note that the side that the symbol shows up on is opposite the side that this is in. So when it's on the opposite side of the line, it's on the near side. If the fillet was on the top only, we'd be welding on the bottom side of this. Down here, down here we have a V-groove weld, no backer bar, so we can see just the puddle on the top. A double bevel V-groove, where this is ground to a point and it's welded on both sides on a double bevel. And a double fillet, where we can see now the fillet is on both sides of the steel, and it's got a fillet weld on the top and a fillet weld on the bottom. Here's an exploded assembly of a bolt beam to column connections. We've got two strips of angle iron or angle steel. They're pre-drilled and bolted in place to these locations. No weld, just a bolted connection, beam to column flange connection. Here's an illustration of a similar one where we have bolted beam to column connections. We have backer bars and welds on the tops of these, and then we have this little what's called a dog bone cut out on both sides. And the reason for that dog bone, that says the flanges of the beam are cut to a dog bone configuration to create a zone of the beam that is slightly weaker in bending moment than the welded connection itself. So if there's a violent earthquake, the beam will deform permanently in this zone while protecting the weld connection against failure. So this is purposely designed to be weaker than the weld connection. So if that needed to twist a little bit or a lot during a storm or an earthquake, you're not going to break your connection here. It would just twist the beam out. So it becomes a safety feature. Here we see that dog bone connection in a real situation where this connection is welded onto these pieces, but and it looks like it hasn't been actually welded yet, but part of it has, and this is designed to just deform before it actually breaks off the column. Two types of structures for the building itself is a rigid core, where we might have an elevator shaft or a stairwell in the center of the building, and it is actually the structural integrity of the entire building, and everything else is built off from that. And then we have a rigid perimeter frame, where all of our structural material for the strength of the building is on the outside of the building. So we have rigid core and we have rigid perimeter. Here's another example of a girder to beam connection. So there's your girder. The bigger one is usually your girder, and your beam comes into it, and this is called coping, where we cope the top flange of the beam and cut it in. Remember those radiuses, that's where those sizes come into place. And then we've got a bolt or bolt weld connection here that holds it in place. So if we have a floor that is being poured on the top of this configuration, we have steel that's supporting it continuously all the way through. Otherwise this would be lower. So putting a cope on those cuts is fairly common. Column connections. We don't have a piece of steel that runs 6 floors. We have to bolt these connections together or weld them together. As the steel goes up in height, it may become smaller. So this just shows us some different methods of connecting column ends together. In this case, we can see we've got a steel plate on the top of this column, and the next column is smaller. So as we go up in height, our columns may get smaller and smaller to both save money and be lighter in weight from a structural standpoint. So these different types of connections will account for those things. And here we see this beam here is smaller, so there's actually a plate in here to make up the distance so we don't end up bending the steel. So that shim plate actually acts as a spacer so that these can be connected all the way to the top. A typical framing plan for a multi-story steel frame building would look something like this. We generally don't see plans drawn for steel framing, and what we're looking at here is in a plan view. We're looking down at this floor assembly. We can see our column assemblies are here, and this particular one doesn't indicate what the size of these columns are, but it does indicate what the size of our girders and our beams are. This is a W30 by 124, so we know immediately this is a 30-inch deep girder that is 124 pounds per linear foot. This beam running into it is an 18-inch deep beam that's 40 pounds per linear foot. You'll notice when it gets to these column lines, it increases the depth of these beams so that they're larger in size. With these left blank, it's just understood that these continue. They may have a letter designation DO on here for basically ditto, meaning that these continue all the way down. So the only place they would change is in these areas where there's some different configuration in here. These openings would be areas where there would be an elevator shaft or a stairwell. So the size of the steel would change. So this basic construction would indicate what size beams. There would be detail sheets then to show how these connections are to be made, whether they're welded, bolted, riveted, however it is. Those would all show up on the detail sheets. But this gives us a good idea of what our framing plan is going to look like. When the steel comes from the manufacturer, it's going to be all marked and labeled. Some of the flanges are already in place, and some of the holes are made. So you can see in this illustration here, this welder is attaching connection plates onto this steel column, and it also comes with these lifting lines, these twin channels bolted to the end, which would allow the crane to hook onto this to lift it up into place. You can see these tabs being welded on are locations where we're going to have steel girders being bolted in to the frame, and also some plates down here on the bottom. So a lot of these things are pre-done in the factory, which makes it even more important that the material be exact, that the drawings be accurate to the point where we can be assured that everything's going to line up. It doesn't always, because we're actually building on the ground. The erector, this is where the fabricator's job ends and the erector's job begins. The gentleman or the people, whoever it happens to be, are going to be up on the high steel. They're going to be bringing this material in. They're hooked off on safety lines. You can see where they're clipping on here to make sure that they're tethered when the steel's being brought into place. We have cranes on the ground that can lift the steel into place from the ground. We also have cranes that actually rise up with the building structure itself. So as this goes up, they can actually lift themselves up with the steel as the building gets higher and higher. Sometimes we just don't have cranes that can reach that high, so you actually have cranes that can be brought up. If you ever get a chance to go onto Hulu and look, or one of the shows MPBN has shown is Super Skyscrapers. There's one on a skyscraper in China that shows these cranes actually lifting themselves up onto the building. And so anyway, we can see he's got some wrenches. What we'll see further on here is we see these are called drift pins. The drift pins, they'll probably have one or two on their belt with a wrench end on one end to kind of get things started. So as the steel gets set in place, they use these drift pins, which are basically tapered needles, to kind of line up the holes on the steel as it gets in place, so they're long enough so that they can kind of work the steel back and forth to make it work. In order to make things accurate, a lot of times at the base of the column we have leveling nuts, so that we're not going to be exact on the concrete. So the concrete may be out half, quarter inch. We want to make sure that it's level at the top, so we do our leveling at the bottom to make sure everything is exactly where it should be. After these are leveled up, we have these threaded rods that come out of the concrete base or column, and there may be a gap in the bottom, and at that point you'd fill this with grout after the construction is in place to make sure that the leveling stays accurate. Here we see a weld symbol, meaning that we've got a fillet weld on the near side here, so this indicates fillet weld on either side of the flange. You can see the width of it here is not all the way around. If there was a circle here, we would see that it would be welded all the way around, but it's not. It's just in certain segments. And you can see they're bringing this steel down. They actually lift up 3 or 4 of these at a time, bring down one, lock it in place, and the next one's ready to go into place. So the steel actually gets put in place pretty rapidly. Here we see an erector putting the bolts into a heavy construction site. There's one of these cranes over here that's dropping the steel into place. These would be considered not really open. There's your open web joists over here, but these would be just heavy trusses that are pre-engineered and pre-manufactured. Here we see a bolt connection on this. Looks like tubular steel actually, as opposed to flange steel, connecting these columns together. This person is welding the open web steel joist to the girders and beams in the steel. The final piece of heavy steel going up is referred to as topping out. The last beam in the steel frame is fairly special. They usually have a little celebration, a topping out ceremony, and it's usually painted yellow or striped or decorative to indicate the last piece of steel to go into place on the building. On top of those open web joists and structures, we have corrugated steel decking that gets laid down and fastened to the top of these joists and beams, and they are to support the floor material. If we look at this, this is what the decking material looks like. It's going to get placed down, fastened to the material, reinforcing steel run across, and concrete poured in place in this particular application. It's not always concrete, could be some other material. Here we see the corrugated decking, the reinforcing steel, and pouring the concrete. These frames that are left out here may be what we call dunnage for holding a piece of air handling equipment, or it could be a future opening that they're going to cut through for an access door or roof hatch. You can see also these studs. These are called shear studs, and they're generally on the column line right above the beam, and they're used to help attach the concrete deck to the steel beam and keep it steady or keep it solid. So these are shear studs. Another method to do this without the corrugated metal is using precast hollow core planks for floor decks. These have some advantages in that they're faster to put in, they're structurally sound, they also give you a place for running wires and cables and things inside these structural planks to a certain extent without weakening them. So we can see the stairwell here going up through the building, and then these structural concrete planks are laid in place. This person is welding a truss T sub-purlin to an open web steel joist, and then this, whoops, sorry about that. He's installing insulation foam board over those truss T sub-purlins, and then some wire reinforced mesh and poured gypsum fill will be installed over the foam boards, creating the upper composite deck. So a lot of this stuff may be put in layers. Fireproofing of steel framing. We generally don't think too much about fireproofing steel framing, but building fires are not hot enough to melt steel, but are often able to weaken it sufficiently to cause structural failure. I think the biggest example we can point out is the World Trade Center. World Trade Center had fireproofing on the beams and columns, but it was in the process of having it removed and replaced when the planes crashed into it because it had contained asbestos, so they were in the process of changing it out. So some of the steel was exposed. Whether that had a significant impact on the collapse of the buildings, I don't know. But building codes generally limit the use of exposed steel framing to buildings of 1 to 5 stories, and where there's taller buildings we need to put fireproofing onto the steel, and that can be accomplished in a number of different ways. Exposed steel can be encased in concrete. It can be enclosed in metal lathe and plaster, similar to this. We're looking at a plan view. It can be enclosed in multiple layers of gypsum, which we see quite often in columns and beams. So if you see a column in a building that looks like it's just a gypsum, most times you're going to find there's a heavy steel beam behind there. We can use spray-on fireproofing. We have loose insulated fill inside a sheet metal enclosure. So this would be just sheet metal enclosing fireproofing. And a water-filled box column made of a wide flange shape with added steel plates. I've never seen this used, but apparently there is. I would think it would get corroded after a while. They probably put chemicals in there, but actually building a water encasement inside the steel. So just something that apparently has been used in the past. Here we see from U.S. Gypsum supplied some illustrations of using fireproofing on these beams and columns. In this case, we've got a column with a couple of steel studs on either side. Looks like a layer of gypboard here, and 2 layers of probably 5/8 inch gypsum around the outside that are metal corner beads, plastered and sealed to provide a specific time fire rating on this particular column. When we put spray, if you look up above a suspended ceiling in a lot of buildings, you'll see sprayed on insulation over the steel beam, which looks kind of nasty. That's why we put a ceiling below it. But in this case, he's using a gauge to measure the depth of the fireproofing to make sure it has significant or enough depth to provide the protection of the steel that is necessary. Now here's another method. Imagine taking a standard W beam, this is looking at it from the side, and cutting it in this fashion, and separating it and staggering the joints and welding them together makes what's called a castellated beam. So it's a way to create a little more strength, but not having to fill in all this material. Trying to extrude a beam that might be 5 feet deep would be difficult. Maybe factories can't do it, but if you need something that deep, you could use something like a castellated, where you can use approximately half the depth of the beam and have it cut and reshaped to create basically a 2-piece beam that's been welded together to create one structural shape. That's referred to as a castellated beam. Standard steel building construction uses a little different configuration in that they custom make these types of structures to save material, be as economical as possible, and be as structurally sound as required by code. Now, one of the things that you don't see on a structure like this is, imagine if you had a large snow load on the top of this roof and it's pushing down on this material. Because these are tapered on the top, it's going to want to bow out. If it got too much weight on it, it might try to push out these bottom flanges and actually spread. So underneath the ground here, these are generally connected with cables, heavy steel cables that run from one side to the other, so that if there is enough pressure on the top, these bottom connections are actually held in place and prevented from spreading out on the bottom. So there's a lot to these buildings that's probably just out of sight, but they are designed to be efficient, less expensive structures for quick erection. They're pre-engineered, so all of the calculations are done ahead of time. So clear span buildings like this can be done relatively cheaply with pre-engineered steel building construction. We have purlins along the sides and across the top that are exterior skin, metal skin material would go onto. Window openings would be framed out and insulation on the inside. They're not the most energy efficient type building because we don't have a lot of thermal break between the inside face and the outside. So there's a lot of places for cold and heat to transfer out. The manufacturing of steel, from a sustainability standpoint, and I won't go through all of this material because it's fairly technical, but if we look at the material it requires to create 1 ton of steel, 3,100 pounds of ore, 300 pounds of limestone, 900 pounds of coke, which is made from coal, 800 pounds of oxygen, and 2,575 pounds of air. And then we've got all the gaseous emissions. But if we look at the embodied energy, the energy that is required to create steel from the beginning, just the manufacturing processes, is about 14,000 BTUs per pound. 14,000 wooden kitchen matches, I like to think, per pound to create 1 pound of steel. It says in modern facilities, scrap steel is typically added as an ingredient during this process, resulting in recycled materials content of 25 to 35%. Most structural steel is made from recycled scrap by the electric arc furnace method. An embodied energy of about 4,000 pounds per pound, or 4,000 BTUs per pound. Less than 1/3 of that of steel made from ore. So there is some energy efficiency in recycling our steel as opposed to creating it from raw materials. In addition, 95% or more of all structural steel used in North American building construction is eventually recycled or reused, which is a very high rate. In one recent year period, 480 million tons of scrap steel were consumed worldwide. We ship a lot of this stuff overseas to the auto manufacturing or the construction, and it's used over there also. Scrap used in the production of structural steel in mini mills usually comes from sources within approximately 300 miles of the mill. So we used to have these giant mills that were centralized in Pittsburgh, and all of the steel went by rail to those locations, was shipped out. Steel is heavy, it's tough to ship, and becomes very expensive. So these mini mills that have sprung up have reduced the need for that, and also kind of helped with the decimation probably of the big mills because of the ability for the smaller mills to meet demand and make it more cheaply. Construction. It's a relatively clean, efficient process. Paints and oils used on steel members can cause oil pollution. Steel frames are lighter in weight than concrete frames to do the same job. Some spray-on fireproofing materials can pollute the air with stray fibers. Steel framing is protected, if protected from water and fire, will last for many generations with little or no maintenance. Steel exposed to the weather needs to be repainted periodically. That's not to say if you go over by the football field and look at the steel supporting the bleachers on the visitor's side, you'll notice that it has a very rusty look to it. And that's actually designed that way. It actually comes as a steel that is designed to almost immediately turn to a rusty color, and that rust actually protects the interior of the steel. So some steel that you look at that looks rusty is actually designed to be that way. Steel frame members and building walls and roofs should be thermally broken or insulated. And I just mentioned that about the steel building, is that finding a way to put a thermal break between the outside and the inside of the steel is a good way to prevent heat loss, because it does transmit the cold so well. We remember my old school that had single pane windows, a lot of them still in the university. If you look in Machine Tool Lab, for instance, has a lot of single pane windows with solid steel windows that are not thermally broken, and you'll see that frost build up on the inside, meaning that there's moisture being attracted to that cold steel and icing up. It just means that we're losing a lot of cold out through these. So having a way to thermally break that, and we're doing it now with our new windows and doors, but some of our older buildings haven't accomplished that, is relatively important. Almost all the material is recycled from steel buildings. And steel seldom causes indoor air quality problems, although surface oils and protective coatings sometimes off-gas and cause discomfort to some occupants. And that is it for steel. Now that is heavy steel framing, talking about columns and beams and girders and purlins. But I think we're also going to be talking light framing.